So there are a lot of diagrams that I'm just not going to copy over from my notes. Instead, I'll just show you my notes, which will also be uploaded. So instead, I'll kind of just walk you through what the diagrams are. I expect we'll finish my first set of notes, which would be the equivalent of lecture 14, early, just because instead of me writing a lot, there's just going to be diagrams that I'll be talking about. I'll do some writing near the end, but because we'll finish early, I'll be able to jump into lecture 15 stuff. So hopefully, depending on how far we get in lecture 15 stuff that would have been gone over on Wednesday, we may be able to save like the last 20 minutes or last half an hour or so of Wednesday's lecture to answer questions for the exam, like as a mini review. I will be holding another exam review probably on Thursday. Yeah, that's probably when I'll hold it. Keep in mind, there is a quiz on Wednesday. So like as usual, obviously there's no homework that's assigned this week, but there's a quiz. So, you know, be ready for that. It's going to cover material from today, from last Friday, from Wednesday, as normal. Right, so let's jump in. Let me share my screen. So I'm just gonna, so this is just my standard lecture notes that I use. It's the OneNote copy of my lecture notes, rather than me writing everything out. Let me open up the chat window. Right, so last time we talked about special process, or we talked about cycles. At the end, we talked about cycles, which are basically just, you start somewhere and you end at the same place, but you go through some sort of thermodynamic process, right? And the idea behind those cycles is that because you start and end in the same place, you can do it over and over again. And so it turns out that, in general, any cycle, assuming the cycle has finite area inside of it, any cycle is going to either consume work, i.e. it will take in work and output heat, or it will take in heat and output work. That just depends on the orientation of the cycle, clockwise or counterclockwise. Now, the reason I say that is in a cycle, the change in total internal energy U, delta U, is 0, and that's because it starts and ends at the same location. One way to see this is that on a PV diagram, if it starts and ends at the same place, then its initial and final pressure and volume are the same. And so we can apply the ideal gas law to get that the initial and final temperatures are the same as well. And from what we know about total internal energy, it's just proportional to the temperature of the system. So if the temperature is the same, then the total internal energy is the same at the beginning and at the end. Hence, no change in total internal energy. And therefore, from the first law of thermodynamics, we get that Q equals W, because remember, the first law of thermodynamics is, just to sketch this, it's delta U equals Q minus W. So if delta U is 0, then Q equals W. So for any cycle, if, say, the work done by the gas is positive, then that means that the heat would be positive, and that means that you are inputting heat into the system. So the reason we care about this is that this is how an engine works, right? You take a system, in the case of a vehicle, it might be, in the case of a vehicle, it might be you have some like gaseous or gasoline vapors rather. You heat them up, they expand because they combust and so on. And so you're adding heat to the system in the form of the exothermic reaction from the gasoline, but that produces work. And so it's useful to understand how these processes work, how these cycles work. And in order to talk about these cycles, we need to first start by talking about 4 special types of processes. So regarding those processes, I'm going to show you a few things. I'm going to show you a picture, basically, of what these processes actually do, like what they would look like in real life, at least schematically. I'm going to show you what the heat and work is going to do. I'm going to show you how the state variables change, and I'm going to show you the relationships between the state variables using what we know about how heat and work are related to total change in internal energy, how the total change in internal energy is related to the constant volume heat capacity, and so on. And then I'm going to give you a diagram. So let's just jump right in. So we're going to start with isochoric processes. Now, this is probably like the easily the most straightforward of the processes that we're going to talk about. So isochor, or rather an isochor or an isochoric process, is a process where the volume of your gas is fixed. You'll see why this naming convention makes sense once we talk about the next type of process. But just for the moment, think isochoric means constant volume. Now we know that when the volume doesn't change, we know that we can automatically know a few things. First, when we first started studying how heat interacts with ideal gases, we considered constant volume cases. So this is kind of the simplest case where there's no work done. And hopefully you guys have a good understanding as to why having delta V being equal to 0 implies that there's no work done. So here's a picture up top. So imagine that this brown thing is a piston, the blue thing is the gas, and the white thing is, say, the atmosphere. So the brown thing is fixed in place by these spikes, so it can't move, meaning that the volume of the gas, like the piston, can't move left or right to change the volume of the gas. So let's just look in this first case here. So in that case, Q is being added to the system. Basically, we're seeing what happens when we put certain constraints on our system, in this case, the constraint being constant volume, and then we do stuff to it, i.e., if we add heat, or if we take away heat, what happens to the rest of the system? So we're going to add heat to a constant volume of gas and see what happens. We know that the volume doesn't change, hence delta V equals 0. So that means that there is no work done. Now, we are adding heat to the gas, so your intuition should say, barring everything else, the energy of the gas, the internal energy of the gas, and the temperature, both of those should increase. We're not allowing anything else to happen. It's perfectly insulated from the environment except from the heat added. This Q is positive. So the temperature and the internal energy should both increase, just from what we know about the first law and so on. And you guys also know that, like, if you, for example, put like a stove or put a pot of water on the stove and you heat it up and you don't let any of the gas escape, maybe you close it, the pressure inside the container will also increase. So this kind of is intuitive, at least, or to say the least. All of these state variables change in predictable ways. And the opposite happens when you remove heat from the gas. That could be via conduction to the walls and then out to the environment or whatever. Now, from the first law of thermodynamics, because the work is 0, sorry, my nose is very itchy. 1 sec, I need to go grab a tissue. Pause the recording. Right, so because the work is 0, the first law of thermodynamics tells us exactly how the total internal energy changes. And in fact, it's just equal to Q in this case, which is not surprising. So this is that case where we have constant volume, and so the heat capacity, or the specific heat, this constant volume specific heat, is really actually related. Typically, it's just written in terms of Q, but it's really actually equal to delta U. And so we can write out those consequences, right? So for a monoatomic gas, by definition, Q is equal to N times CV times delta T. That's just, by definition, what CV means. And so for a monoatomic gas, that CV is 3/2 R. And so we can actually do some quick replacements. Note that if you have PV equals nRT, and V is constant, then delta PV, which would be equal to delta nRT, would be delta P times V equals nR delta T. That's where this equation comes from. And so they're just replacing nR delta T with delta P times V. So what this does is it lets us calculate the change in pressure given the amount of heat added, if you know the volume and so on. And you can do the exact same thing for a diatomic molecule. So this is the, perhaps another way that we could have gone about this without knowing this fact is by using the kinetic theory of gases to get that delta U is equal to 3/2 nRT for a monoatomic gas, 5/2 nR delta T for a diatomic gas, and so on. And then relate that using, oh, what just happened? Relate that using the first law of thermodynamics to Q. And then that could get us to a definition of this constant volume mass-specific heat capacity. Sorry, molar-specific heat capacity. And as we've covered in previous lectures, that constant volume molar-specific heat is just 1/2 times R. Remember, R is just a number, it's like 8.41, times the number of modes available to that type of molecule. So for a monoatomic gas, it's 3, for a cold diatomic gas, it's 5, and so on. Now, just as a quick way to grasp these processes, I'm also going to give you some diagrams. So these are PV diagrams for when you add heat. So in this case, we have Q going in, and for when you take away heat, you have Q coming out. So it's not necessarily true that vertical lines means only heat is exchanged, but I mean, for the most part, if you have a process that's a vertical line on a PV diagram, that means there is no work. So as long as there's some sort of change in internal energy, you have to have some heat. Right. So that's what those diagrams, or that's what an isochoric process looks like on a PV diagram, and it kind of makes sense because the volume's not changing. So the only thing that could be changing is pressure. So if you were to plot that, the set of all points where the volume is constant is a vertical line. Right. So that's an isochoric process. They're relatively straightforward. You can use these relationships that delta U is equal to Q, and what you know about Q being related to the constant volume specific heat, molar specific heat, and what you know about the structure of the molecules to learn a lot about these systems. And automatically W is 0, so we don't need to worry about that. The next type is, and I promised that isochoric would make more sense later, the next type is called an isobaric process. Now you guys probably know that like a barometer is a thing that's used to measure pressure, right? Like air pressure. So isobaric means iso, meaning constant or same, and baric meaning related to pressure. So this is a constant pressure process. That's what an isobaric process is. So if we go back and we look at an isochoric process, iso, again, meaning same, choric meaning related to volume or related to size. So an isochoric process or an isochore is a constant volume process, whereas an isobaric process is a constant pressure process, meaning that we keep the pressure of our gas fixed while we allow the volume to do whatever it's going to do. So this one's more complicated. So let's examine this a little bit more closely. So here we have a diagram. So the way that we keep the volume or the pressure of a gas constant is by allowing the piston to move. So let's say that inside, before we added the heat, let's say that inside was, say, 2 atmospheres of pressure. 1 atmosphere of pressure is something like 100,000 pascals, which is the SI unit of pressure. But outside, it's just air, which has just a pressure of 1 atmosphere of pressure. So if there's a difference in pressure on the 2 sides of the piston, that means that there's a greater force on one side, because pressure is just force over area, than on the other side. And hence, the gas on the inside, because it has more pressure, will push the piston out. And it'll push the piston out until the pressure on the inside is the same as the pressure on the outside, at which point it'll stop pushing on the piston. So the way that we make an isobaric process happen is we just allow the piston to freely move in the atmosphere, and then we just add heat. And we will add heat, and some of that heat will go towards heating up the gas, right? But not all of it. Some of that heat will go towards doing work to push the piston away, to expand the gas. And in fact, this is kind of the basis for a lot of engines, right? The idea is that you add heat to the system, and that heat, some of it heats up the stuff in your system, like it heats up the vapors in the air and so on. But some of the energy goes towards pushing a piston up. And the reason we want to push that piston up is because moving that piston can then push on other things, which might make things rotate and drive an engine. So let's look at what happens when we add heat to a constant pressure system. So we're adding heat, so Q should be 0. Now, we automatically know that if we're adding heat, so the assumption here is that we start at equilibrium, meaning initially the gas inside the system has the same pressure as the gas outside the system. So the piston's just happy where it is. And then you add heat. And so the moment you add heat, that means that the volume is going to change, right? So the volume the volume starts to change because you're adding heat, which increases, which would want to increase the pressure, but the pressure has to stay constant, and it does so by pushing the piston away. So the volume increases even though the pressure is constant. Now, what can we say about the temperature and the change in internal energy? Well, we know that if the temperature changes, the internal energy changes. That's just a true fact because internal energy and temperature are just directly proportional. So you could feasibly imagine that the temperature stays the same, right? It could be the case. Maybe it would be the case that the temperature would stay the same, perhaps. But certainly the temperature wouldn't decrease by adding heat to the system, right? That doesn't agree with our intuition. It's certainly not true. And there's good mathematical reason, but it requires kind of going in the backwards direction from the way we're going. So certainly the temperature is either constant or increases. And I propose to you that the temperature has to increase. Now, there's a way to see this, and it's by using the first law of thermodynamics and how the pressure relates, how the change in volume times the pressure relates to the energy. So before we actually prove that delta T and delta U are both greater than 0, let's actually go and talk about the first law and its consequences. So the first law of thermodynamics is just delta U equals Q minus W. Now, so far, we don't know that delta U isn't 0, but so ignore this sentence for a minute. We're gonna get to why that's the case in a minute. But just bear with me. So Q from the first law of thermodynamics is equal to delta U plus W. It's just a rewriting. Now we have a formula for delta U. This is true for any type of gas. It's the number of modes divided by 2, so 3/2 divided by 2, times nR delta T. Now if delta T is 0, that thing is 0, right? So that's what delta U is. Whether that's 0 or not, we're agnostic about so far. And then we add P times delta V. Now, we've said in the past that the work done is actually an integral of P dV. But because pressure is constant, you guys know how to integrate. Like if I gave you this integral, 5 dx, you know that that's just 5 times, and let's say it's, 1 to 3. You know that's 5 times 3 minus 1, or 5 times the change in x, right? So anytime you integrate a constant against some other changing quantity, dV in this case, you just multiply that constant number, in this case p, times the change in your variable. So the work done is just P delta V. Now, we're almost done. This is P delta V. So what is P delta V? Well, let's go back and look at the ideal gas law. We have PV equals nRT, right? So again, I'm going to stick a delta in front of the whole thing. This is a trick that we do a lot because it's technically correct, and it's allowed mathematically, so because you can always do the same thing to both sides, right? So you guys remember the product rule from calculus? The product rule from calculus is that if you take the derivative of a product of things like f times g, then it's f times the derivative of g plus g times the derivative of f, right? So the same type of rule applies for deltas as it does for d's. Like if I just took d on PB, it would be p dv plus v dp. That's still true. And the same applies for deltas as well. So in this case, this left-hand side is actually, because the pressure doesn't change, because delta P is 0, this left-hand side is P delta V is equal to little n and r are both constant, nr delta T, right? So we can make this substitution here into P delta V by using the ideal gas law. From there, we now have an equation that is 3/2 nr delta T plus nr delta T. And simplifying, we get 5/2 nr delta T. So the reason why I went through all of this is to say that Q is equal to something that's proportional to delta T. So if we add heat to our system, if Q is indeed positive, then delta T also has to be positive. And what that implies is that delta U is positive. So that's why it cannot be the case that if you add heat to the system, that your temperature doesn't change. That's just not possible for an ideal gas, assuming constant pressure. And then you can do this identical argument for a diatomic molecule as well. It just becomes 7/2 because the total internal energy is 5/2 because it has 5 modes for a cold diatomic gas. And so, in fact, we learned something new. For a constant pressure system, which an isobaric process is, we have a new formula for Q. We have Q is equal to a number times R, so it's equal to N, which is there, Cp, which is just 5/2 R, times delta T. Now, what is this Cp? Well, Cv was the constant volume molar specific heat. Cp is just constant pressure molar specific heat, meaning it is the amount of energy required to increase the temperature of an ideal gas by 1 degree Celsius for 1 mole of that gas, if you hold the pressure of that gas constant, not the volume. And that's not surprising that the numbers are different. You have to add more energy if you're holding the pressure constant, because some of that energy that you're adding is going towards expanding the gas and hence is doing work. So you're losing some of that energy. And in fact, based off of the calculation that we did here, that we did with the monoatomic gas, it's actually fairly straightforward to see that this Cp is related to the Cv, which was 3/2 R, or 5/2 R. It's just 3/2 R plus R, or 5/2 R plus R, right? So it turns out, and this is true provably for any type of ideal gas, that Cp, the amount of energy to add to 1 mole, the amount of heat to add to 1 mole of a gas at constant pressure in order to raise it 1 degree Celsius is 8.31 or 8.41 joules more than the amount of energy required to add to 1 mole of a gas at constant volume to raise it 1 degree at constant volume. You have to add more energy to get the same temperature change. And again, as I said, it makes sense because some of that energy is going towards expanding the gas. By the way, I know I'm graffitiing up these notes. I don't think I'm going to leave the graffiti on when I publish them, just because it looks messy. So hopefully you guys have this sort of thing in your notes, or you can go back and watch the lecture and you'll see it. Right, so we've already done a whole lot of work, but we can now relatively easily, or we were able to relatively easily, draw the PV diagram for an isobaric process as well. So isobaric means constant pressure, means that volume's changing. So an isobaric process, an example of one, would be the pressure is constant, i.e. it's on a horizontal line on your graph, and the volume is changing. And then the work is just the area of the rectangle, right? That's what we found out about work. Work is just the area under the curve. In this case, the curve is a straight line, so it's a rectangle. Right, so now there's some more work to do. I want to actually tell you a little bit about this Cp. So here I defined Cp, right? Cp, or I showed you a way to calculate Cp and why it's called Cp. It's the constant pressure molar specific heat. It's the amount of heat needed to add to a system to raise 1 mole of it by 1 degree Celsius. So what we saw was that the constant pressure molar specific heat is 8.41 joules per joules per mole Kelvin, higher than the Cv, the constant volume specific heat, molar specific heat, which is a nice nifty fact. And so that means that if you know what a substance is made out of, i.e. you know what its molecular structure is, then you can just figure out what Cv is. Cv is just the number of modes that an atom has divided by 2 times R, right? So because Cp depends only on Cv, then a given molecule has a well-defined, the values of Cp and of Cv just depend on the molecular structure. And so you can characterize the you can characterize the type of molecule by taking the ratio of these quantities. And the reason why we want to take the ratio is because both of these quantities have units. And so a natural way to characterize something ought not depend on how we measure that thing, right? So if we take the ratio of these things, call that ratio gamma, take Cp divided by Cv, then each different type of molecule will have a different value of gamma. And the gamma is just a number. It doesn't have units or anything. So in this case, for a monoatomic gas, Cp is equal to 3/2 R. This is for monoatomic. Cp is 3/2 R plus R, and Cv is 3/2 R. I should have probably gone backwards, right? So Cp is 5/2, or is 5/2 R. Cv is 3/2 R. So the ratio is 5/3. Similarly, you can see for a cold diatomic molecule, Cp would be 7/2 R. Cv would be 5/2 R, because there are 5 modes. There's the 3 translational kinetic energy modes and 2 rotational kinetic energy modes, assuming the vibrational modes are frozen out. So there's 5 modes in that case. And so in that case, 5/2 R plus R would be 7/2 R. So 7/2 R divided by 5/2 R is 7/5. So notice that these two numbers are different. They're both unitless numbers, but they're different. So if you find a gas with a gamma, which can be measured just by doing experiments, with a gamma of 5/3, then you know it's monoatomic. You find a gas with a gamma of 7/5, you know it's a cold diatomic gas. Similarly, a polyatomic gas, again, a cold polyatomic gas, would be found to have a gamma of 4/3. And this can be relatively easily explained away. For the, well, it's 6/2 and 8/2, hence 4/3. When I say polyatomic, I mean something with 3 translational kinetic energy modes and 3 rotational kinetic energy modes and no other modes. Assuming, so maybe this would be, I should write cold here as well. Right, so that's what gamma is. I know that you guys needed that for your lab, so that's how gamma is defined. It shows up in other processes too, but it's a useful constant for characterizing the type of molecule. So that's why we introduce it here, and it'll actually show up in a more complicated process in a minute. So before we continue to the next type of process, does anyone have questions? Take that as a no. Okay, so that's isochoric, constant volume, and isobaric, constant pressure processes. There are 2 others that show up and are super relevant and important. The first one is the isothermal process. So an isothermal process is kind of exactly what it sounds. Iso meaning constant or same, thermal meaning relating to temperature. So an isothermal process, or an isotherm, is a process where the temperature is constant. Now, we know that if you just leave a gas alone in an insulated box and don't let anything happen to it, it will be in an isothermal state. Its temperature will be constant because nothing will happen to it. That's not the type of process we're talking about, because that's a non-process. We're still talking about things happening to the system, meaning that we still want either the system to do work or the system to have heat added or whatever. Now, so let's start with what we know. Isothermal processes must have constant temperature, which by definition, not by definition, by the relationship between internal energy and thermal energy and temperature, the change in total thermal energy has to be 0. So from the first law, delta U is equal to 0. So if it's to be the case that anything is to happen, if you add some amount of heat, some amount of work has to be done. So if we want anything to happen, i.e. if we want any work to be done or any heat to be added or anything, they both have to be present. So in this case, let's just consider the case where Q is greater than 0. We could have considered the case where Q is less than 0, as we could have in all of these previous cases, by the way. All of these processes are reversible, so you can do the reverse process, just has the opposite effect. But let's consider the case where we add thermal energy Q. Well, from the first law of thermodynamics, if Q is positive, then W has to be positive. So that means that when you add heat to the system, all of that energy leaves in the form of work, which sounds like a great deal, right? Because it means that you can just take heat and just convert it automatically all to work and make useful energy out of it. Technically, it's not like this. That's true, but just not particularly useful. Now, what has to happen in this type of process? Well, certainly, if you're adding heat to the system, and we've concluded that the work done, therefore, is positive, that means that the volume must increase. Now, there's a hitch here. What happens to the pressure? Does the pressure increase, decrease, or stay the same? Well, we know the volume increases. If the volume increases and the pressure increases, that would indicate that something is going wrong. Like, if the internal energy of the system, so you guys know that, like, if you increase the pressure and keep everything fixed, that would correspond to an increase in energy. Similarly, if you increase the volume and keep everything fixed, that would correspond to an increase in energy, just because if the volume increases, then the temperature increases, assuming the pressure is fixed. So if we increase the volume and increase the pressure, that would seem to indicate that the internal energy should increase. So, but we know that the thermal energy shouldn't be increasing. In fact, it should be constant. And in fact, if we increase the volume but didn't let the pressure change, that would still increase the thermal energy. So in order to have the thermal energy not increase, in order to have delta U be 0, we need to have the pressure decrease. And then it's just a balancing act between the volume increasing and the pressure decreasing. This should kind of be familiar. Like, if you increase the volume of something, its pressure should decrease. And one way to view that is that the pressure is really just a matter of the force from the molecules bouncing off the walls. And so if you're increasing the volume but keeping the energy the same, the energy being how much kinetic energy each particle has, that means that the speed that it bounces off the walls with is the same, but the walls are getting further apart. So that means that there's more time between bounces, and hence the average pressure would be lower. So delta P should go down. Right, okay, so let's talk about consequences then. So we've already established that if delta U is 0, then that means that Q is equal to W. All the heat that goes in is equal to the work that comes out. So that means that we can calculate the heat just by calculating the work. We know how to calculate work. Relatively straightforwardly, it's just the area under the PV curve. So let's skip over and look at what this curve looks like. We'll get to the consequences in a minute. So in a PV diagram, your state always has to obey PV equals nRT. That always has to be true. Now, for an isothermal process, that if the temperature isn't changing, that means, using the ideal gas law, if N, R, and T are constants, that means that P times V is a constant. In particular, P, as a function of V, is equal to nRT divided by V, right? This is not P times V, by the way, it's P as a function of V. So in this case, we just have the formula for how P varies with volume because temperature is fixed. Typically, this temperature would have to be a function of volume as well, but we know that the temperature is constant here. So we can just write it as T. And so what this looks like is, this is P goes as 1 over V with some constants thrown in. This is an inverse function graph. It just looks like your standard, this guy. And so we can plot that. This is what it looks like when you add heat to the system because the volume increases. And so we can actually, I mean, that's what an isothermal process is. It's a very specific curve. It's the curve that behaves precisely as 1 over V, with multiplied by, or where the pressure is proportional to 1 over V anyway. And now you might be wondering how we actually do this integral, but it's actually a lot easier than you think, because the work, or how to find the area, right? The area is just the work, the work is just the area under the curve. But it's actually relatively straightforward, right? We know what P is in terms of V, in which case it just becomes an integral, just a regular old integral. It's just the integral of nRT, nRT is a constant so we can pull it out, of our function P, times the integral from your initial volume to your final volume of dV divided by V. Just a regular old integral, right? You guys know how to do this. That integral works out to be the natural log. And then you do the appropriate, like natural log of Vf minus natural log of V naught. That's equal to natural log of Vf divided by V naught. It's just a log trick. And so what we get is that the Q and the work is equal to nRT times the logarithm of Vf over V naught. Now this is the natural log, of course. And by the way, we can relate that quantity to the natural log of P naught over Pf. And that's just because P is proportional to 1 over V that we get that relationship. Now, there's an important message here. This doesn't care about the type of gas. And the reason that happened was because in the 2 previous processes, one of the things that we needed to do to find, say, the change in internal energy or the work done or whatever, was we needed to calculate Q. Or alternatively, we needed to calculate delta U. Both of those things depend explicitly on the type of molecule, right? This is that whole business of delta U or the internal energy cares about how many modes of energy that each molecule has. This is the Equipartition Theorem. So, because there is automatically a way to calculate Q from this process just by calculating work, we don't need to invoke at all the type of molecule, and because delta U is 0. We don't need to invoke the type of molecule at all, and so there should be no dependence on that type of information, the number of modes, in this calculation. And indeed, that's what happens. We don't care at all. The work done and the heat required for an isothermal process is completely agnostic about the type of molecule that is undergoing that process. It only cares about the change in volume, or the ratio of the final to initial volume, or equivalently the ratio of the final to initial, the initial to final pressures. Obviously, it cares about like the number of moles that you have as well, and the temperature. So this is a fairly common process, especially processes that happen very slowly. So when, for example, consider this case where you're doing work on a system and heat is coming out. So consider you have a piston, or actually, let's just say you have a syringe, right? You have a syringe filled with air. Now, the syringe is made of plastic, so it doesn't conduct heat very well to the outside world. But if you stop off one end of the syringe, so that it's just a sealed system, and then you push very, very, very slowly on the end of the syringe to make its volume shrink, if you push sufficiently slowly that the air inside has time to exchange heat with the outside to keep it always at room temperature, that would be an example of an isothermal process. Because all of the work that you're doing, that you would typically be doing to add energy to the gas, is completely removed by conduction of heat to the outside environment. So isothermal processes typically happen slowly, because they require that heat is being transferred to or transferred away from the system at a rate equal to the work that's done. And work can typically be transferred, or work can typically be done a lot more quickly than heat can be transferred, which is why these processes occur slowly, because the limiting factor is the heat added or the heat removed. Right, so there's one final type of process that shows up frequently. It's the final special process, and it's called the adiabatic process. Now, I don't actually have a good understanding as to why it's called the adiabatic process. The word adiabatic, or the phrase adiabatic process, or an adiabat, which is another name for an adiabatic process, shows up a lot in physics. Typically, it means that the system is closed. It's closed to the environment from, like, it's thermally insulated. And so that kind of thing does show up in a lot of approximations. But let's just talk about the mechanics of it. So imagine that you had something that was really hot, like a really hot gas, inside of a piston that was completely thermally isolated from the rest of the universe. Meaning, like, the gas inside is 1,000 Kelvin or something, but it's in a perfect insulating container, except there's a piston. So that gas, in general, hot gases tend to expand, especially if the pressure is held at a constant, especially if they're allowed to expand, right? So what would happen is that hot gas, because none of that thermal energy can leave in the form of heat, that thermal energy will push the gas, hot gases tend to be high pressure, will push the piston out. So an adiabatic process is a process where there's no heat entering or leaving the system. So an isochoric process is a process where there's no work being done on or by the system. An adiabatic process is like the opposite. There's no heat entering or leaving the system. It's thermally isolated. It is, what's the word? Insulated. It is insulated from the environment, perfectly insulated. And so the only thing that can leave or enter the system is energy via work. So, and that's why there's like this purple line around it to indicate that it's insulated perfectly. So let's say we start with a hot gas, right? We know the hot gas will push the piston out and do work. So we know that the work will be positive. From the first law of thermodynamics, if Q is 0, that means, and the work done is positive, that means that delta U, which is negative W because Q is 0, has to be negative, right? Because the work done was positive. Because the change in internal energy is negative, and there's that direct correlation between between internal energy and temperature, the change in temperature has to be negative, i.e. the temperature of your system decreases. Kind of makes sense. That energy, which was kind of stored in the form of temperature, is being used to expand the gas, and so some of that energy goes away and the temperature decreases. Now we also know that the pressure would decrease because, again, that pressure is being used, the pressure that is due to the temperature, that pressure is being used to expand the gas. And because the gas is expanding, or because work is being done by the gas, the volume is positive. So that explains all of the state variables. And it's it's relatively easy to understand anyway, at least from an intuitive perspective. Before we continue, I want to talk about this example of doing work on the gas but keeping it thermally insulated so that you perform an adiabatic process. So the example of a syringe filled with gas is actually a really easy example to use for an adiabatic process. Because the syringe is made of plastic, it tends to be very poorly insulating. Sorry, it tends to be very good at insulating. It insulates very well from the environment. So it's a good approximation of this purple box, which perfectly insulates. So, and like I said before, for an isothermal process, you have to go very, very slowly because the limiting factor is the rate at which heat can flow through the barrier. But if you're looking to prevent any heat from flowing through the barrier, instead, you do this very, very quickly, and so that the heat doesn't have time to leave the system via the container. And you may say, wait a minute, but Sam, I thought we said that all processes that we care about are slow. This is the one exception. So adiabatic processes can always be in equilibrium, even when they're fast, as long as the piston doesn't accelerate. So a good approximation of this would be a very, very sudden acceleration and then a constant velocity. Once you have constant velocity, then the gas will always be in thermal equilibrium It's acceleration that would cause a lack of thermal equilibrium. Think of it this way. If you accelerate, you'll have a bunching up of oh, Jesus. You accelerate, you'll have a bunching up of gas molecules near the piston, and so it'll be higher pressure in one region than in the other, because it's accelerating, and so it's kind of accumulating gas particles on it. But if it's traveling at a constant velocity, you won't have that bunching up, because you'll form a new equilibrium where that bunching up is precisely canceled, or that bunching up will be eliminated, because the gas molecules can react at the same rate that the piston is moving. So going back to the syringe, what you do is you close off one end of the syringe, you have your plunger in the other, and then you suddenly slam it shut. It's a good approximation of an adiabatic process. And so what would happen is you're doing a lot of work on the gas inside, and what happens is that the air inside the gas, inside the syringe, heats up a lot, heats up very dramatically. And in fact, this would be a good lab demo if I had them. And it's a common demo to do when we talk about adiabatic processes. Put a piece of paper in a plastic syringe, close off one end, and expand the plunger out a lot, and then just slam it shut, and you can get the paper to light on fire, because the temperature of the gas inside the syringe increases so much, because all of the work that you do gets converted to thermal energy, because none of that escapes as heat. So it's actually like the most efficient way to convert work to internal energy of a system. And it can happen very quickly. So they're used very frequently in real life processes when you need to increase a system's temperature by doing work on it. Right, okay. So that's why an adiabatic process is relevant. Let's actually do some math on it now. So we already established that delta U is equal to negative W. Now, there's some calculations that are involved here. Not very hard ones. The work, we know what the formula for delta U is. Delta U is always equal to N times CB times delta T. That's just always true. And because the work is equal to negative delta U, we can just plug that in. So for a monoatomic gas, the work done by the gas is negative 3/2 NR delta T. Now here's where the math gets a little bit funky. So right now, it's not quite clear how we can relate this quantity to the quantities on a PV diagram. But bear with me. We have PV equals nRT for an ideal gas. So NR delta T, which is equal to delta nRT, is equal to delta PV. And so instead of factoring or distributing that delta through, we just compute the change in the product of P times V. So NR delta T is equal to delta PV. So the work done is negative 3/2 times the change in the product of P and V. Or equivalently, it's just equal to 3/2 times the initial product, P naught times V naught, minus the final product, PF times VF. Similarly, similarly, we could do the same thing for a diatomic gas, and we find it's 5/2. Now, this is where gamma shows up again. Now, these numbers, this 3, this 5, those are just the number of modes in the molecule, but we now have a better way of characterizing the structure of the molecule. Rather than talking about, oh, how many different modes of motion does this molecule have, now we can just say, this molecule has a gamma of this number. Monoatomic gas has a gamma of 5/3. Diatomic cold gases have gammas of 7/5, and so on. And so you can actually relate the number of modes divided by 2 to gamma. In fact, it's equal to 1 divided by 1 minus gamma. Sorry, gamma minus 1. And this is relatively straightforward to show. It's basically just number of modes over 2 is equal to CV divided by R. Then we can go, well, so now let's compare these quantities. So 1 over gamma minus 1 is equal to 1 over gamma is Cp over Cv minus 1, which is 1 over Cv plus R over Cv minus 1. This is a bit of a mess. Actually, you know what? Instead of me doing this, because it's kind of a waste of time at this point, you guys see the steps. If you don't believe me, go check it yourself. I don't want to spend 10 minutes working out the algebra. The point is it shouldn't be surprising. If you make gamma closer to 1, which happens as you increase the number of modes, right? 5/3 is bigger than 7/2. If you make gamma closer to 1, then 1 divided by that number, 1 divided by 1 minus gamma, gets larger. And so the number of modes gets larger as well. That's all. And the math checks out that this is the formula it takes. So if you want to find the work done by an adiabatic process, it is related to the final pressure, the final volume, the initial pressure, the initial volume, and the structure of the molecule, this gamma factor. Notice, by the way, that gamma is never 1. It can't be 1. That would mean that the number of modes, that would mean that the number of, it can't be 1 because Cp is by definition larger than Cv. It can be close to 1, but it can't be equal to 1. Right, so I think that almost takes us through to the end of what I had for today. I can, let's just continue with me writing, so I go a little bit more slowly now. Actually, I don't think it takes us through to the end. That we have not. It's not that close. So one moment, let me just change over to my lecture notes, and I'll just start the standard style lecturing now. Right. So hopefully you guys have all of those images in your notes now. And if not, you can go, well, if not, I will reference them if I need to. So up until now, and as I mentioned, an adiabatic process can be very quick. And that's just this requirement that the piston doesn't accelerate. So it now takes a little bit of work to actually show the equations, for example, for calculating the, like, say, the pressure in, so how do I want to phrase this? So for the other equations, for the other types of processes, we had things like, oh, well, for an isochoric process, it was a vertical line. For an isobaric process, it was a horizontal line. For an isothermal process, it was a line that followed the path that where P is equal to nRT divided by V. Right? What's the equation that describes an adiabatic process? That's a useful thing to have because A, it will help you plot these things. B, it will help you understand how the pressure and volume are related to each other in an adiabatic process. And it's another example of where gamma shows up. We want P in terms of V. So unlike the other cases require just a smidge of calculus. This actually requires some more complicated calculus. So let's start with the equation of state. That is PV equals nRT. Right? So starting with the equation of state, let's look at small changes. So this is similar to what we did to get the total work done, but we're gonna work infinitesimally so that we can actually we can do some integral calculus and work out what the equation is. So so infinitesimally changing, D on PV is equal to D on nRT. So this is like the infinitesimals that you learned about in calculus, right? And so D, like I mentioned earlier, has this product rule property that it distributes to both terms. So this is V dP, that's the first term, plus P dV, which is equal to N and R are constants. This is N R dt. Okay, that's a useful statement. Now, what about the infinitesimal first law? Because we need to use the infinitesimal first law here to make this useful. So the infinitesimal first law can be written as du equals dq minus dw. Now, as a caveat here, very important caveat, this is not a small change in q, not a small change in w. Those are not state variables, they don't change. It's a small amount of q, it's a small amount of w. Whereas this d, maybe I'll put a slash through these. This is a small amount, whereas d is a small change. So if you add a small amount of heat and the system does a small amount of work, then the internal energy will change by a small amount. For an adiabatic process, zero heat is added, zero heat is removed. So not even a small amount, just zero. So we can use what we know about U, which is NCVT. We can use that to get a relationship about du. That is, NCVDT is equal to negative dW. Now, dW, a small amount of work, we've talked about this. This is when we first derived work done by a gas, that's just P times dV. So this is negative P dV. So, solving, we get that dt, the small change in temperature, let me put a slash through here again, the small change in temperature, dt, can be given by negative P dV divided by NCV. I know that this is a lot of work so far. It seems like we're not going anywhere, but I promise this will go somewhere. So we can take that and we can plug it in up here. So taking that, bringing it back down, what do we get? We get that V dP plus P dV is equal to negative, oh, what just happened? Oh, it just minimized. Is equal to, well, what cancels? So the N will cancel, and there will be an R up top and a CV on bottom. So this is negative R divided by CV times P dV. Okay, let's rearrange. We get that V dP plus 1 plus R over CV times P dV equals 0, right? But we can simplify this. V dP plus, well, we can just combine fractions. 1 plus R over CV is CV plus R over CV P dV, which is just this thing here is how gamma is defined, right? The numerator is Cp by definition. The denominator is Cv, so this is V dP plus gamma P dV equals 0. Gamma, again, is just a number. So then I'm going to do some standard differential equation tricks. I think you guys may have seen this before in a calculus class, but if not, all I'm going to do is I'm just going to start moving things around, treating things as if I'm allowed to, like, I'm just going to rearrange things. So we get V dP is equal to negative gamma P dV. I'm going to divide both sides by V and P. So this becomes dP divided by P equals negative gamma dV divided by V. Hope everybody's followed so far. And this is where we want to, it's not where we're going to stop, but this is kind of like the useful equation that we get out of this. Now, all we do is we just slap an integral sign on both sides, which you're always allowed to do the same thing to both sides. So we get dP divided by P equals negative gamma dV divided by V. Gamma is a constant, so I can pull it out of the integral. Now these are indefinite integrals, just is what it is. So I'm gonna just, they'll both get a constant, right? But I'm just gonna absorb the constant and like put it over here. So I'm gonna put the constant only on one side. So this is log of P is equal to negative gamma log of V plus, say, this is just alpha. It's just some constant. It's just an integration constant. I don't want to use C because, you know, that's already taken. So I'm going to rearrange this again. I'm going to add this to the other side. Log of P plus gamma log of V equals alpha. And now I'm going to use some log rules. Remember that if you have a coefficient in front of your log, you can bring it up top, and then when you add together two logs, they multiply. So this is log of P times V to the gamma equals alpha. Or rewriting, we get that P is equal to, so actually let me just be a little bit more explicit so you guys can follow it more easily. I'm going to exponentiate both sides. P times V to the gamma equals E to the alpha. I'm just going to define E to the alpha as beta. Just to, because it's just a constant. We don't know what the constant is, so we can, it just is what it is. And so what we get is we get that P as a function of V is equal to beta times V to the negative gamma. I know it's a lot of work to get there, but this tells us how the pressure changes with volume during an adiabatic process. So in particular, what we learn is that the shape depends on the type of gas. Right? The function changes for the different gases. It's not like an isobaric or an isochoric or an isothermal process, where the shape is just what the shape is, and then the values might depend on the gas. In this case, the shape explicitly depends on the type of gas. On top of that, gamma is always greater than 1. So that means that P of V is never equal to beta divided by gamma. Sorry, beta divided by V, i.e. it's never identical to an isotherm. If gamma was 1, that would mean that beta times V to the minus 1 would just be beta divided by V, which is exactly the formula that we would expect from an isothermal process. So, so adiabats are always distinct from isotherms. They might only differ by a little bit because gamma might be very, very close to 1. It might be, you know, 9/7 or something, or whatever. But the point is it is always, gamma is always greater than 1. Right. So all of the things that we've talked about, up to and including adiabats and this formula, in addition to the ideal gas law, can be used to solve problems. For example, if I gave you a problem that was, let's say I said, and I'll just walk you through this. We have a PV diagram, and I tell you that there's an adiabatic process that looks like this. By the way, the adiabatic processes and isothermal processes on a graph tend to look similar, at least in isolation. They both are like curved and going down, but they are distinct. So if I tell you that this is an adiabatic process, and then I give you, say, V naught P naught, and V1 P1, what can you learn about the type of molecule here? Well, you can actually learn a lot, right? Because the shape of an adiabatic process depends on the type of molecule. And so really, if we write down our general formula for an adiabatic process, it's beta times v to the minus gamma. There's only two unknowns here. In like, if you know nothing about the system, there's only two unknowns, right? So just like how a line, y equals mx plus b, if you're given 2 points, you can determine both m and b. If you're given 2 points in an adiabatic process, you can determine both beta and gamma, just straight up by doing algebra, because you have 2 points means you have two relationships, i.e. you have p naught equals beta times v naught to the negative gamma, and you have p1 equals beta v1 to the negative gamma. So you can do algebra to them to solve for both beta and gamma. And so beta is just a number. It just is basically a constant coefficient that relates the number, that involves things like the number of moles, and it involves things like unit conversions from volume to pressure with some power and so on. It's just a number. But gamma tells you a lot. It tells you the type of molecule, right? If we find that, say, that gamma is approximately 7/5, oftentimes in these types of problems, it won't be exact. If it's approximately 7/5, then that means you know that the molecule is a cold diatom. Because gamma is unique for different types of molecules. Sorry, sneezed. Right. Yeah, and so you can actually learn just from a PV diagram in 2 points what type of molecule it is. Hint, hint. That is certainly a question I've asked on an exam before. Determine the type of molecule based off of this process. I don't know if I'll include that question, but I've included that type of question before, where it involves doing some algebra. I'm not going to do the algebra for you because, you know, that would be too easy. Then you would just go look at you because it's open note anyway. But it's not a hard thing to do. But this is how you would do it. That is one type of problem. You can also, for example, if you know the type of molecule, but you don't know the no, how do I want to phrase? Basically, given enough information on a PV diagram, you can learn everything from how many molecules you have, or how much the temperature increased by during a process, or what the molecule's made out of, or a whole bunch of various things once you know the algebraic relationship between P and V for various diagrams, for various processes. It's like, it's almost amazing how much you can learn just from knowing what type of process is happening. Right, so we still have about half an hour, so I'm actually going to get a jump on Wednesday's material, because that will allow us to use Wednesday as a partial review session. So let's jump right in there. Does anyone have questions about any of these processes before I continue? There must be some, because at least this adiabatic business can be awfully confusing. Allison, that's a really good question. In general, ideal gases don't really care about the type, about like the atoms for the molecules that make up the molecules, as long as they have the same structure. So there is something to be said that, for example, a diatomic molecule like N2 will have a different threshold temperature at which the vibrational modes turn on for the, as opposed to, say, O2, another diatomic molecule. But the mode counting only depends, like which types of modes could be present, only depends on the shape of the molecule. So as long as the shape of the molecule is the same, it doesn't, like, none of these things matter. So let's say that you have a mix of oxygen, O2, and nitrogen, N2, maybe in a ratio of 23 or 21% oxygen, 73% nitrogen. and then a mix of other trace things. Like atmospheric air, by the way. That is basically the mixture of atmospheric air. At normal room temperatures, neither the diatomic nor neither the O2 or N2 have their vibrational modes really active at all. And so it turns out that because they both effectively have the same number of modes, that's the only thing that matters for any of these processes, including adiabatic processes and the values of gamma. Gamma only cares at all about the constant pressure molar specific heat and the constant volume molar specific heat. Constant pressure molar specific heat only cares about the constant volume molar specific heat. So let me write a dependency diagram. So gamma, so the number of modes is the same for O2 and N2 at room temperature, but that tells us what CV is, and that tells us what CP is, and those two things together tell us what gamma is. So as long as they have the same number of modes, then they'll have the same gamma, period. Doesn't matter what they're made out of. So even if it's a mixed gas, as long as the elements of the mixed gas have the same number of modes, then you can treat them as if it's just a uniform gas. Now things get more complicated when you have a mixture of different types of molecules with different modes, different numbers of modes. And so then you actually have to treat them as separate systems that don't interact with each other, and then their pressures are additive and so on and so forth. And then you don't talk about the gamma of the whole system, you talk about the gamma of the individual parts. And it gets a little bit more complicated. Does that make sense? Okay, so does anyone, unless anybody else has any other questions, maybe mark yes under the participants tab if you do, so then I know to wait. Unless anyone has any questions, I'm gonna move on to Wednesday's material so we can get through that, or we can go through as much as we can. All right, so I promised at the beginning of lecture today that what we would talk about is we would talk about cycles. I mentioned how on Friday we started talking about cycles, and the reason we care about cycles is because they're like actually physically useful from an engineering perspective. So far, we've only talked about processes, but we know that processes make up cycles. So if you slap together a whole bunch of these processes together, or if you slap together a whole bunch of these processes, you can make a cycle of however you want. So we're going to talk about today, or for the rest of today, applications of thermodynamic processes. Now, some people say processes, but I think that sounds ridiculous, so I say processes, even though I'm not British. I also say perseverance, and it makes my wife mad. So, funny story about me, I guess. Anyway, so let's talk about engines, and in particular, thermal efficiency. So that's where we're going to start, and we'll spend probably the rest of today on that, maybe some of Wednesday. So I need to define what an engine is for you. An engine, God, my nose is so runny, is a device that follows a cyclic thermodynamic process. Cyclic? By the way, I'm abbreviating thermodynamic with thermo. That results in heat being converted into work. So the example that I gave at the beginning of lecture, you send in, you take heat, maybe it's from an exothermic reaction of gasoline combusting. You take heat and you convert that into work. Seems like a reasonable definition of an engine. So let me give you an example of a very, very, very simple engine. So we would have, so engines and in general cycles can be modeled or can be described by the path that they take on a PV diagram, assuming that they use gas as their working fluid. So we have P and we have V. So an engine could be as simple as this square being our cycle. So we would have P2, P1, V1, and V2. And maybe A, B, C, and D. So in this case, for a single cycle, it's always true that delta U equals 0, because you start and end at the same pressure and volume. And from the ideal gas law, PV equals nRT. If the initial P is the same as the final P, and the initial V is the same as the final V, then the initial T will be the same as the final T. So the change in thermal energy is 0. This is equal to Q minus W. By the way, that doesn't mean that an engine is an isothermal process, because it's not. So just because the temperature, final initial temperatures are the same, that doesn't make the whole thing isothermal. An isothermal process is when the temperature stays the same throughout the entire process. Right, so what this means is the net Q in, we'll put net here, is equal to the net work out. I say net because it might require a little bit of work in to get more work out, for example, or it might require a lot of Q in and then some Q out. Now we know that the work done, but the total work for one cycle, which is the net work, it's the work in minus the work out, it's just the area of the square. So it's P2 minus P1 times V2 minus V1. And so Q in, so there we go. This is the work out, which is equal to the energy that we had to put in. Like, this is great. It tells us how much heat do you need to add to a system that has this type of process. Now, this is a great example, but it doesn't resemble a real engine. And the reason why it doesn't is because the real world is not generally quasi-static. Some parts can be, like, you can very closely approximate an adiabatic process in the real world. You can also very closely approximate other processes, but it's just, like, real engines are more complicated. So let me show you schematically what a real engine is, what a real engine does. Scheme has an E. A real engine does the following. You have some reservoir of high temperature. So this is a hot reservoir, maybe with some temperature TH. And then you have some of that energy, call it QH, go into the working system. Maybe that's like a box containing gas of some sort. And so the hot reservoir takes, no, that shouldn't be a 4. It gives heat to the working system because it's hotter than the working system. That working system takes some of that heat and converts it to work, which is what we care about. But the rest of that energy goes to a cold reservoir. Call it TC. And so this cycle goes something like this direction. You add heat, some work comes out, you dump the rest of the heat to your cold reservoir. Then you add more heat, some work comes out, then you dump the rest of your heat to your cold reservoir, and so on. So one way to think about this would be have your system be constant pressure. You add heat to it at constant pressure. That does some work, but now the gas is a little bit hotter because we saw that if you add heat to the system in a constant pressure environment, it does get hotter. So you need to cool the gas down back to its original temperature. So to do that, you put it in contact with something that's colder than it to bring its temperature back down to that cold temperature. And then you can restart your process. However, some of that heat that leaves the working system, call it QC, that's gone. Any QH, I can't write an H, any QH that becomes QC is wasted. It heats up the environment, or the cold reservoir, which then would heat up the environment. Heats up the environment instead of doing work. Like, think that, like, one example of a cold reservoir would just be air. Air approximately has a fixed temperature, and there's enough of it that it'll always stay the same temperature regardless of how big your engine is. So if you just air cool your thing, that QC is going to the air, and that's excess energy that you don't get to use. And this wasted QC is a source of inefficiency. I mean, we don't typically like inefficiencies, but they're a real part of thermodynamics and how the real world works. So I'm going to define the quantity E, which is thermal efficiency. And by the way, all of these calculations we're doing completely neglects like friction and things like that. So this is assuming your mechanical engineers are perfect, there's still some inefficiency. So the thermal efficiency is defined as work, the work out, divided by the amount of heat that came in. The amount of heat that came from the hot reservoir. And using the first law of thermodynamics, that's equal to the amount of heat that came in minus the amount of heat that left, divided by the amount of heat that came in. Or, again, rewriting, this is just 1 divided by minus QC over QH. And I'm putting absolute values here because, in general, QH is going to be positive because it's energy entering the system. QC will be negative because it's energy leaving the system, and so on. So we're just talking raw numbers here. So this is how we can define thermal efficiency. And the way that we calculate QC and QH, or work and all those things, those are all going to be dependent on the type of cycle that we model. So let me give an example of, or a good approximation of a real world engine. We're going to talk about the Otto cycle, also known as the Otto cycle. And I say also known as because it's spelled differently. It's a very convenient name because this is a model for the internal combustion engine, the one that makes automobiles move. Hence, Otto cycle as opposed to Otto. Otto was the name of the guy. Otto meaning automobile. Anyway, so here's what the diagram for an Otto cycle looks like. So you have your P, you have your V. So start off with A down here. Large volume means your pistons are fully expanded. And by the way, the order doesn't actually matter. You go up to B. From A to B, so from A to B, this is defined to be adiabatic expansion. So you have high pressure in an insulated environment, or it's just a very quick process. You have high pressure and it causes your gas to expand. It pushes the piston up. Then you have a constant volume. Let me make this just a smidge taller. Actually, no, I don't need to do that. Constant volume heating. Let me put C over here. Now that's Q. C. So from B to C, that would be isochoric heating, constant volume. So we know that no heat enters the system in an adiabatic process. However, we do know that if you isochorically increase the pressure in your region, that is isochoric. Sorry, if you increase the pressure without changing the volume, that's isochoric heating. So we know that heat, that's a terrible arrow. This is where heat enters the system from the hot reservoir. So from B to C, that's when the gas explodes. And it produces a lot of heat, which causes the gas to expand. Sorry, which increases the pressure in the gas. From there, we have, let me get this right. We have from C to D, this is adiabatic expansion. So now the pressure was increased very rapidly and to a very high value because you heated up the gas a lot by exploding the gas, by burning it, by combusting it. And then, and so the volume increases adiabatically because it's very high pressure, very high temperature, and so it pushes the piston up. So this is like the piston upstroke. This is the piston downstroke over here. And in neither of those strokes, because they, wouldn't A to B be compression? Yeah. Oh, sorry. Yeah, I wrote expansion. It should be compression. It's compression in my notes. I just misread it. So we know that an internal combustion engine happens or cycles thousands of times per second. That's good because the faster the process, the less time there is for heat to enter or leave the system, which means that it can be well approximated by an adiabatic process. In this case, again, the combustion happens very quickly, so it won't be perfectly isochoric because the combustion is not a quasi-static process, but it's an approximation we can make. So then from C to D, we have adiabatic expansion, and then from D to A, that is, from D to A is when we have the waste heat being dumped. This is isochoric cooling. So this happens, so the gas rapidly expands and then it hangs for a bit at the top of the stroke. And during that time, the hot gas is vented. The hot gas is vented and new cool gas is, or in this case, air, perhaps mixed with some gasoline, is injected into the system. So it's not quite actually the same thing as isochoric cooling, but it fills the same role, meaning we take the hot gas and replace it with gas that's identical in every way, except now it's cold. And so the pressure decreases as we do that. And then the cycle, but now it's low pressure, but still high volume, and so the cycle continues. The piston comes back down, and it's the piston downstroke, and we have that the cycle repeats. And so actually, it is here the isochoric cooling that we have the heat being dumped. So you have the hot gas being removed from the system, and cold gas coming in from outside the system, usually just air. And then you inject gasoline maybe at point A, or sorry, at point B. The point is it's at that time that the heat that was in the system, it's not actually, like, it's not conducting heat to another system. We're just taking that system and replacing it with another system that has already lost that heat, which is effectively the same thing. So I'm going to call this V min. I'm going to call this V max. By the way, for those of you who are interested in cars, this is what I mean when I say I understand how an internal combustion engine works. Doesn't mean I can rebuild one. So this V max, we call it equal to R times V min. This R here is the compression ratio. Is how much larger the piston expands to compared to its minimum volume. So what's the efficiency here? I just want to note here, by the way, that this E that we're about to calculate is an upper limit. So a real engine, parts of the cycle B to C and D to A are not actually quasi-static. They're not reversible. So in general, you will have lower efficiency from this engine in a real-world engine. And on top of that, there's things like friction, and there's other more complicating factors. So what we're about to calculate, this efficiency, and it's not going to be 100%, this efficiency that we're about to calculate is an upper limit for the efficiency of an internal combustion engine. So in order to calculate this, we need the following quantities. We need QH and QC. So QH, well, we actually know how to calculate the heat input, or the heat the amount of heat added or removed from a system during an isochoric process. That is, it's just N times CV times the absolute value of TC minus TB. Similarly, QC, this is the energy that's dumped to the environment, is N times CV times absolute value of TD minus TA. So what do we get? We get that E is equal to, I'm using the 1 minus QC over QH formula here, 1 minus NCV, and we know which temperature is higher, so we can get rid of the absolute values, TD minus TA divided by NCV TC minus TB. They have, like, it's the same type of gas and during both processes, so they have the same CV. So this is equal to 1 minus TD minus TA over TC minus TB. Great, okay, so this tells us something about the efficiency, but it's not quite there because it's not a particularly useful formula yet. We define, so this is a recall, how the compression ratio is defined. R is equal to Vmax over Vmin. And Vmax is the volume at either A or D, and Vmin is the volume at either B or C. So this is VA or D divided by VB or C. And now we can relate those temperatures, and we can relate the temperatures to the volumes. So another recall, T, actually no, this is not a recall, this is a note. T times V to the gamma minus 1 is a constant for adiabatic processes. Why is that? Well, we know that P times V to the negative gamma equals constant. Oh, that was weird. We also know that for an ideal gas, we have P is equal to nRT divided by V. So that implies, we can just replace P with nRT divided by V. That implies T times V to the gamma minus 1. Sorry, that's P to the gamma, not P to the negative gamma, equals constant. That's why that happens. So for an adiabatic process, you can also write a formula for temperature in terms of volume. So we can use this fact that there's just a constant that's equal to the product of temperature and volume to the gamma minus 1 to relate the temperatures and the volumes during the adiabatic process. So that gives us that TA, so one of the adiabatic processes is from A to B. So TA times VA to the gamma minus 1 is equal to TB times VB to the gamma minus 1, because those are in the same process. Similarly, TC times VC to the gamma minus 1 is equal to TD times VD to the gamma minus 1. Okay, so far so good. And so we can do some algebra to these two equations, to get a formula for TD in terms of TC. TD is equal to TC times VC over VD to the gamma minus 1. But VC divided by VD is equal to 1 over the compression ratio. So this is equal to TC times R to the 1 minus gamma. I'm just switching the sign, gamma minus 1 to 1 minus gamma, because it's the inverse. So that's what TD is equal to. Similarly, oh boy. Similarly, we get that TA is equal to TB times R to the 1 minus gamma. Just by using the fact that these are adiabatic processes. So that means that TD minus TA, by the way, the reason we're doing this is because we want to figure out how these quantities relate to each other, given what we know about the process. TD minus TA is equal to TC minus TB times r to the 1 minus gamma, right? I just factored out r to the 1 minus gamma. Or, put another way, that implies that the efficiency is equal to 1 minus r to the 1 minus gamma. So that is, given the makeup of our air in this case is basically diatomic, so gamma is basically 7/5. Given the makeup of air, you get an upper limit on the Otto cycle using, depending on what the compression ratio of your cycle is. So a typical values for an ideal Otto cycle, it's about 50%. Real gasoline engines aren't quite as good, again, because that was an upper bound on efficiency. Real gasoline engines have an efficiency of, by the way, efficiency can be, it's a number between 0 and 1, and so you can write it in terms of a percentage. It's typically about 35% for the really good ones. So clearly real gasoline engines aren't as good as your best Otto cycles, or for an ideal Otto cycle. Like if you take a gasoline engine and you give the value of R that you would need for that particular engine, and then you plug in the correct value of gamma and so on, you would get about 50%. For gasoline engines, for the real equivalent, you would get a slightly lower value. Right, so I think that that's where I'm gonna stop today. We'll continue next time talking more about more special types of cycles. But yeah, let's stop the lecture there, and let me probe if anyone